Any other questions?
Oh, we be looking at
The lab notebooks?
yeah.
Just yeah, day of the final, or you can turn it in. Now,
Wow. What is that?
this is gonna be just a demo.
Huh?
We'll do that in a little bit.
A demo?
Yeah, you could leave it to the side, Laura. You have to set it up.
Okay, check the connection here.
I'm sorry.
Check the connection here.
Well, do we have the potassium iodide one? The YouTube? The potassium iodide? Okay, let's continue here with this. So, what makes a nucleus stable or unstable? And so they're trying to take some observations to see if they can figure out what was going on. And so these are the observations. The magic numbers are just unusually stable nuclei, which have a very high binding energy for nucleon. And so there's something special about the magic numbers. But you know, something like this is, you know, a lot of people get results versus discussion mixed up. You know, what are results and what are discussion? And so a lot of people in the results for the formal lab write-up were doing things like percent yield or whatever else. No, that stuff doesn't belong there. The stuff that belongs in results is just the facts of the experiment. You know, the factual results. You know, the things that cannot be disputed, right? And so the results of this would be that, yeah, these combinations here have high binding energy. Well, that's bad. But is it a fact that, you know, these combinations correspond to shells in the nucleus? Is that a fact that there's shells in the nucleus? Well, yeah, maybe not. You know, that's somebody's hypothesis, right? If there's very widespread agreement and everybody agrees with that hypothesis, then we call it a theory. Right? And the theory should go on to predict new, unforeseen results. So based on this theory, we should be able to make predictions for things, you know, that we don't necessarily or haven't observed, don't necessarily know. And so this is the results, and then the analysis of the discussion might be something about shell theory, or the shell hypothesis. And then we have even odd, you know. No, the island of stability came up from something else. Yeah. The island of stability comes up from, you know, because if you look at this, you know, eventually we're going to hit a point where we'll have too many protons, you know, and but well, we'll talk about the island of stability in a minute. But here, even odd, you know, this is just factual data or results. You know, what's the hypothesis here? You know, could you incorporate this into some kind of shell theory, perhaps? So, there are other observations, and the other observations are the blue dots here. The blue dots are like naturally occurring isotopes. And so with this, we see, you know, these naturally occurring isotopes means that these are stable. Whereas if we veer off from here, we could get radioactive isotopes. So for example, if you look, this ends here. This ends here, and the nuclei get too big, and nothing's stable above this, right? And so typically, these are just too big, and they'll undergo alpha emission to get back down to the region of stability. The island of stability is another region up here, which is hypothesized to be stable. And actually, somebody made one recently, or not too long ago, in the island of stability. island stability is not a non-radioactive isotope. It's still going to be radioactive, but it should have a much higher half-life. But these are, in the delta stability are non-radioactive. These have stable nuclei.
Do you know that last one up there at the top, the last dot, is that radon? At 86?
It shouldn't be radon, because radon
Yeah.
is...
The one before that is 18 or... Somewhere right there.
It looks like it. It looks like it to be radon, huh?
That's what I'm saying, but I thought it was radioactive. That's all.
Well, radon is radioactive. Well, that's a good question, John.
Trying to see the scale.
Yeah.
What they had it to.
That would be up here. And so I guess what this does is it would include radon here. And so let me take that back. These are not all non-radioactive. Radon would be radioactive. Radon's unstable, but radon has a half-life of 10 to the minus 3 here. And so it's somewhat long-lived. But still, if you look at the average atomic mass of radon, it's still 222. So there's no good data on that. Well, the exact definition, I don't know how they define it. I always thought it was the stable nuclei. If we veer off one way or the other, for example, if we have too many neutrons or too many protons, then it becomes unstable. And so what this is showing is that we need a certain number of neutrons for every proton. And it looks like for lighter elements, we need 1 neutron for every proton. And that leads to stable nuclei. As the nuclei get heavier and heavier, then the ratio becomes more like 1.1 neutrons for every proton, as it becomes a little steeper here. But if we have too many neutrons, then we have to get rid of the neutrons. One way to get rid of neutrons is to convert a neutron into a proton. If we convert a neutron into a proton, that's beta emission, so they'll shift it to the right. If we have too many protons and not enough neutrons, then we can convert the protons into neutrons using positron emission or electron capture. And so this is the typical nuclear process that occurs in regions outside the belt of stability. They really don't, apparently, the particle physicists have the nucleus pretty well sorted out according to some of the talks I've seen. But, exactly what the picture is difficult to visualize, But they have it where they can make numerous predictions, because there are other predictions that you'd like to make. If you know this theory, you would like to know what the mass is,